Hey guys, this is Andrew with HKN, and today I'm going to talk about signal space. This is the beginning of a multi-part video series where I'm going to show you how to build a simple transmitter receiver channel simulation in MatLab. But first, I need to explain to you some of the theory that goes into it. So the first thing is a little thing that we use in digital decision theory for communications. And it's called signal space and how to create an orthogonal basis signal set. So what that basically means is when we're sending zeros and ones, we don't actually send a 0 or 1. We send some signal to represent 0 or 1. So for our case here, I'm not saying that this is a good way to do it, but for our case here, we have S0 is a pulse of length of height 1 for time t. And S1 is a pulse of height 2 for time t over 2. And for all intents and purposes, we're going to say that t is 2 seconds. So you send a pulse for 2 seconds of height 1 if you want to send a 0, and a pulse of height 2 for 1 second if you want to send a 1. So at any particular time instance, you can look at the height and you can tell what's happening. Here, we have, we get a signal. Well, that's what we're going to denote as R of t here. That's the signal that we get back. And we find that we end up with a thing of 1.5 height for a length of 2 seconds. And so that's not either 0 or 1. So what do we do with that? So how do we decide whether we sent a 0 or 1? Well, you can kind of look at it and say, well, it's the same length as our 0, and it's only a little bit higher, so we probably sent a 0. And that's good. That's what we want to do. We want to kind of find the one that it's closest to. But because we're engineers and because we want to do this in a computer, we have to do this mathematically and with some numbers. We have to be able to put a number on closeness. And so how do we do that? Well, the kind of intuitive way to do it is we know that closeness is very related to distance. And where do we find distance? Well, we find distance in vectors a lot. So we can take some inspiration from vectors. So if we have a vector like this, and then another vector like this, and then a third vector that looks like this, the distance between them, so if this is, let's say, vector 1, this is vector 2, and this is vector 3, and we want to find which one vector 3 is closest to, well, you can do vector 1 minus vector 3 and look at the magnitude of that, and that will look at our distance. So that's that vector. And we could do vector 2 minus vector 3 magnitude, and that will get us that vector. So that will tell us whichever one of these is bigger is the one that's further away from V3. So if we could somehow vectorize our signals here, then we could put them into this kind of signal space and look at which one's closer. So we could put this one, this one, this one. So for instance, this would be V3, and these two would be V1 and V2. And we could look at which one V3 is closest to. So that seems like a good way to do it, and that's actually the way we do it. We actually use this thing, it's called signal space. And so in order to do this, we need to be able to place these things onto an axis. So we have to define what that axis is. Another way to say that is from linear algebra. We need to create a basis set for this. So for instance, in R3, which is our normal third degree Euclidean space, we have our basis, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So from that, we can make every vector in all space. So we call basis phi. So phi 1 is 1, 0, 0 in R3. Phi 2 is 0, 1, 0 in R3. And phi 3 is 0, 0, 1 in R3. And so what defines these as a basis is that we can make any vector, v sub n, as a linear combination of these other vectors. So we have A, B, C as just being numbers, real numbers. And so if we take those, multiply them by our basis, and add them together, we can get anywhere. We can get Vn as being an element of R3, and it also spans R3. And the other thing we need is we need that if we take the dot product of any basis vector with any other basis vector, this should equal to 1 if m is equal to n. So if they are the same vector, it should equal 1. And if they're not, it should equal 0. So you can see that very quickly here, that in vector form, that this works out. But how do we define any of this for time-varying signals? Well, the first thing we want to do is we would like to be able to define what the dot product of two signals is. So doing that, we say that the dot product of two signals, I'll say phi n of t dot phi m of t, is equal to the integral over a single period of phi n of t times phi m of t. So we're just going to take a multiplication inside this integral, and we'll call that our dot product for signals. So just to see if this is a good way to define it, we can check that very quickly with sine and cosine. So we know that sine and cosine should be orthogonal to each other, meaning that if I do this dot product, I should get 0. So if I do this, I integrate from 0 to 2 pi of cos t times sine t dt. Well, this is the same as the integral from 0 to 2 pi of 1 over 2, the sine of 2t by a half angle or double angle formula. And so then, if we take this integral, what you'll find is that we do end up, in fact, getting 0. So that's very nice for us. So it shows that cosine and sine are orthogonal to each other by our definition, which is what we need. So the next thing that we need to do is we need to create this process for a general signal set. And so the signal set is very similar. Once we have this dot product defined, there's something called Gram-Schmidt orthogonalization. And so that's just a process of making right-angled orthogonal vectors. And you should have learned it when you learned basis sets in linear algebra. But if you didn't, that's fine. You can look up how to do it. But that's actually not what we're going to use today. We're actually just going to use what's called eyeballing it, or just very colloquially called that. You basically just kind of look at it, look at the functions that you have, and you can kind of tell what the orthogonal basis should be. And I'll show you a 4-instance case of that. Just going to erase this very quickly. OK. So for our example here, the basis sets would be these. So we would have phi 0 of t, and that would be a pulse out to t over 2, and it would have height a. And the second one would be a pulse from t over 2 out to t of height b. So we don't know what these heights are quite yet, because those will be defined later. But the reason that we picked this is we can build every single one of these signals out of these building blocks. For instance, we can build S1 of t by just multiplying this by 2 over a. And we can build S0 over t by multiplying them both by 1 over a and 1 over b respectively, and then adding them together. So we can build these sets out of things like that, and you can do something very similar for R of t. The other reason we picked these is that they're very easy to see that these are orthogonal to each other. So if you take phi 0 of t and then phi 1 of t and multiply them, we see that they're never both non-zero at the same time. So we end up with the integral being just an integral of zeros over a full period, which tells us that this are going to be orthogonal, because if you take that integral, you're going to get 0. So if you dot product these two, you get 0, which means they're orthogonal. But we have the other case that if you dot product these two together, you have to end up with 1. If you dot product them with themselves, they have to end up with 1, which is why we don't know what these are yet. But we can solve for those very quickly. So if we take the integral of phi 0 squared of t dt, which is also coincidentally the energy in here, we should get 1. So we want a unit energy signal. So basically what we're doing is we're taking the integral from 0 to t over 2 of a squared dt. And if you carry out this integral, you should end up with a equals square root 2 over t. And to save you the trouble, what actually ends up happening here is that you end up with the same thing, because it's a pulse of the same length and the same form. You should also end up with b equals the square root of t over 2. If you carry out the integral from t over 2 to t of b squared dt, it ends up being the same thing, and setting it equal to 1. So we now know what these heights have to be. So let's fill that in very quickly. We need a and b to both be of heights square root 2 over t. And in our case here, where t is 2 seconds, these are both equal to 1. Hope that made sense. We just had to make these normalized, which is what we did there by making them have to dot product to themselves. So the next thing we have to do is express our base signals, S0 and S1, in our signal space. So we're going to redraw our signal space over here. So the signal space, because we have two basis vectors or basis signals here, is going to look like R2. So you're just going to have two coordinate axes. So this will be the phi 0 axis, and this will be the phi 1 axis. So if we had to build S0 out of these signals, we would say that S0 is equal to, well, it should just be phi 0 plus phi 1. Right? Because we have 1 and a 1, and for the whole time, so if we just add them together, we should end up with this. So that's S0 of t, so these would all have of t's on them. And so we will then express the S0 vector as being 1, 1. So there's 1 multiplied by this and 1 multiplied by this. So we get our S0 vector is 1, 1. So drawing that in here, we get this guy here. So this is S0. And that's 1. And that's 1. Doing the same thing for S1, this is very easy to see that we only need phi 0, but we do need to multiply it by 2. So S1 of t is going to equal to 2 phi 0 of t plus 0 phi 1 of t, meaning that the S1 vector can be written as 2, 0. Putting that into signal space, we end up with something like this, where out here is 2. So this is S1. So we now have our base signals, what was sent, mapped into signal space. So now let's map what we have here, and then we can kind of start doing our distance calculation. So we need to place the r of t vector in here, which means we need to find out what kind of projection this has. What you're going to find is that r of t should equal to a linear combination of phi 1 of t and phi 2 of t. Sorry, phi 0 and phi 1 of t. But you're also going to have some extra bit on the end here. That's actually c of t. And this will not map onto either of the basis sets. This will be some extra. That's not going to happen here, but you can imagine that if this was a little bit more rigid in some cases, if it had a little bit of noise on it, which you could expect in a communication channel, that none of this would map nicely to just flat bars. And so we kind of just ignore this because we know that this is noise because it doesn't match any of the things that we know was the information we sent. So we ignore the extra bit there. So we project r of t onto our orthogonal basis set, which means that we want to write r of t as r of t dot phi 0 of t times phi 0 of t plus r of t dot phi 1 of t times phi 1 of t. So this will get us a number for the amount of RT projected onto our phi 0, and then we know it's in the phi 0 direction, so we just multiply by our unit phi 0. Do the same thing for phi 1, and this can be extended to however many basis signals you need to express however many binary numbers you're sending. So you could actually send 4, 5, 6 binary signals. You would just probably need more bases. It's not a one-to-one relationship, so just because we have 2 here doesn't mean we have 2 here. But it's however many you need to make this combination of signals. So here we have this, and then we'll have that extra bit, that c of t on the end, that we're going to ignore. And so we need to calculate, we need to carry this out. But and so you could do that by actually taking this dot product. But very nicely, we really don't need to take that dot product here. It's actually just very nice that we can build these signals very easily out of just some multiplication. So if phi 0 is 1, and this is 1.5, that means that our contribution A here should be 1.5. And if phi 1 is 1, and it's 1.5 for that time as well, then we know that B should equal 1.5 as well. I hope that makes sense. You would just scale these up, put them on the same graph, and you end up with r of t. So that means that we can express our projected r vector as 1/2, or 3 over 2, 3 over 2. So if we're going to plot that into our signal space here, it would be along the same way here. It's still 45 degrees. But it's actually just extended out a little more to 3 by 2, 3 by 2. So we have our 3 vectors here, R, S0, and S1. So now we can talk about which signal is closest. So the distance vectors here are, well, this is the first distance vector. So this guy is S0 minus R. And then we have another distance vector that goes here, which is S1 minus R. So how do we find which one's bigger? Well, we just have to actually subtract these numbers in their vectorized form, and then look at the magnitude of it, and that will tell us the distance. We very often look at the magnitude squared, And the reason for that being is that if a distance is bigger than another, then its distance squared will also be bigger. So it saves us having to take a square root in the Pythagorean theorem that we need to do to find the magnitude of these vectors. So let's just look at that. Let's look at the magnitude of S0 minus R in vector form squared. And so that should just be 1 minus 3/2 squared plus 1 minus 3/2 squared. So this gives us a half squared is a fourth, plus a half squared is a fourth. So that's a fourth plus a fourth, which is 1/2. So this is our distance that R, our received signal, is from being a 0. Let's do the same thing for 1. So we have S1 minus R in vector forms squared. And so that should be 2 minus 3/2 squared plus 0 minus 3/2 squared. So this gets us a fourth because it's a half squared. This gets us 9/4. So we do a fourth plus 9/4 is 10/4, which is also 2/5. So we end up with 5/2. And so that's our distance between 1 and R squared in our signal space. So at this point, we use what's called a minimum distance decision, or a map decision, which is maximum a posteriori. So that's knowing that we sent these with the prior probabilities that we sent these, that they are even. So we know that we're equally likely to send either one of these. So given that, the one that's more likely to have been sent is this guy here, S0. So at the receiving end, what we decide is that if we get this signal, R of t, we know that maybe something weird happened in transmission, but what we meant to do, we decide that what was meant to be sent was a 0. So as your decoder, your decoder does all this, and he decides that I wanted to have sent a 0. So that's how signal space and decision in binary signals works. I hope you guys learned something, and have a nice day.